Hey, so this is Joe, and this is the first video in the 9th chapter of Stewart's Calculus, and we're going to be talking about logistic growth as a differential equation. So before we go into logistic growth, we've talked a little bit about differential equations in a previous chapter when I was in my video about exponential growth and decay. However, right now I'm going to give you just a little bit of background on differential equations in order to move forward with logistic growth. So a differential equation is an equation that relates some part of one of a function's derivatives to either another one of that function's derivatives or that function itself. So kind of the simplest form of a differential equation is going to be the derivative of x is equal to, or is proportional to, that function of x, where k is just a constant. And so a solution is some f of x, is some f of x that satisfies this equation. So when it's only the first derivative being related to the function, we can say that this is a separable differential equation, because we can write this as dy dx is equal to k times y, and basically we can separate this derivative right here, and so we'll get dy over y is equal to k times dx, and then both of these we can integrate and we'll get out an expression y equals some function of x eventually, and then there's going to be a plus c there because this is going to be the general solution, and the general solution means that there can be technically infinite solutions, because if you add constants and shift that function, it'll still satisfy this differential equation right here, but just with a different constant. So it's a general solution. But you can also look at this and try to just pick out a particular solution that will satisfy this or any other differential equation. Now, we also have differential equations that relate different derivatives to the function. For example, the second derivative of y with respect to x is proportional to y. Now this we cannot separate because we don't know, you can't separate this derivative right here. You could, this is an example of a second degree differential equation that we could just look at and think really hard, okay, what function can we take the second derivative out of, namely like a trig function or a function with e in it. But and so we could kind of guess and check at that, but finding the general solution to this in an algebraic way, as we do with separable differential equations, is not really possible. So in this course, in single variable calculus, I guess until you actually get to your differential equations class, we're really only going to be dealing with, or at least on the AP, you're only going to have to deal with separable differential equations that you can do this kind of analysis on. And also, unless we're approximating a differential equation, which we will do in this chapter, or you're allowed to use the integrals here will be evaluatable. You will be able to evaluate those integrals, because that's also a problem with differential equations that we can get, is we might run into an integral that we just can't evaluate using the methods that we learn in this class. So you can remember that on the AP, if you see a differential equation, either you'll be able to separate it and solve it, you'll be able to separate it, solve it, and evaluate all the integrals in it, or you'll be approximating that. But you won't have to kind of guess and check and figure out a second degree differential equation or another kind of differential equation that you won't be able to solve. But so this is the basic idea behind differential equations. Now, we've already seen, and actually we've solved and walked through the steps to solve the differential equation for natural growth. And if you remember, it's basically the function that what I just showed you. You have like some population, the rate of which changes with respect to time, and it's going to be proportional to the amount of the population that's present. So we'd get kp, then we'd separate it out. When we integrate, we get a natural log on one side. We've seen that before. However, in nature a lot, what happens, and not in nature, but in nature, but in other things as well, we have these cases where there's the best example is you have a population of animals living in a certain area, and that area has only so many resources to satisfy so many animals living there. So if you have less than that kind of limit amount, we call that a carrying capacity, and we can symbolize it by M. So if the population is less than M, so we've got P is less than M, then the population will continue to grow. And if the population is equal to M, the population will stop growing. And if the population is greater than M, the population will actually decrease until it reaches M. So when P equals M, we call that equilibrium. And when P is less than M, that's growth. And when P is less than M, that's decay. So cases like this aren't just straight natural growth, because natural growth is purely either exponential growth or decay, and that just depends on the sign of the K right there. But logistic growth, which is described by this, has this carrying capacity and this equilibrium, and so the growth or decay is proportional to the amount present. So this relationship is in here, but there's also this limit, this carrying capacity, to which the population will reach equilibrium if it's either greater than or less than that carrying capacity. So the way we express logistic growth, we express it as a differential equation. So the rate of change of the population is equal to, or is proportional to the amount present, times, and now we've got 1 minus P over M. And this, and your book has the algebraic proof for this, but I'm just going to give you the conceptual kind of idea. So this part is what satisfies these conditions right here. So M is the carrying capacity for like the population, or it could be money, or whatever. So if you've got P being less than M, this coefficient right here is going to be greater than 0. And so you multiply that by the natural growth equation, and you will get a positive K value right here. So the population, the derivative is going to be positive, so that means the population will be growing. If you've got P being equal to M, this will turn into a 0, and the derivative will be 0. So the population won't be growing at all, which hence equilibrium. And if P is greater than M, if the population is greater than the carrying capacity, then this coefficient right here will be negative. That means the K is going to be negative. That means the derivative is going to be negative, and a negative derivative means decay. It means something's getting smaller, the population's getting smaller, which makes sense, because when we look at these logistic equations, you'll get this, or you can get this, or you can get this, or you can get this. You can technically have infinite solutions to this, because, right, this is a differential equation. We're going to get out a plus C. So there can be infinite solutions, and you can get the solutions where P is greater than M for most of the time, and it comes down to this line, this equilibrium line, because the derivative is negative, and so you'll get a function that decreases. And if you have a case where P is less than M, the function's going to be increasing, looking like this, and infinite shifts could happen depending on prior conditions once we solve this differential equation, but they all converge at this equilibrium line, and this line represents the carrying capacity equilibrium. Everything ends up converging here. If we were to do kind of limit analysis on this, we would find that everything would converge to the same point. So now that we've got a kind of conceptual understanding about what logistic growth is, let's solve this differential equation. And this is the same deal with natural growth. you have to do this solving and separating out this separable differential equation, because it is separable, it's first degree, because we're only dealing with the first derivative, and then the function itself, population. You do need to separate that out for all free response problems, and then use the kind of general solution that we'll find at the end afterwards. But if you memorize the general solution to this differential equation and you're on the multiple choice portion, just jump straight to that to save yourself some time. So on the next screen, let's separate this differential equation out and solve it. So first thing to remember, right, is our goal is to find an expression of p in terms of t. So we're going to separate this derivative, and we are going to isolate the p's and the t's on one side. So we're going to get p times 1 minus p over m down there under the dp, and we're going to get k dt on this side because that's the only t. So to make this a little easier, let's say multiply this fraction by m over m, and we'll get m dp over p times m minus p is equal to k dt. And so now we can integrate both sides. We've got what variable with respect to which we're integrating on both sides, and we can do this. And if you recognize that the form of this equation right here, we can use our partial fractions method to integrate it. So let's go up here and write that out. We're going to solve the partial fractions for it, because remember, we've got two functions of p in the denominator multiplied by one another, and then some polynomial, actually just a constant, up there. So that's going to be equal to a times p, a over p, sorry, plus b over m minus p. And so we multiply this over by both sides, and we get our expression m minus p times a plus p b. And now we're going to have to do our little selective choosing for values of p, because remember, that is our variable. So if we get p is equal to m, the a disappears, and we got m is equal to m times b. We divide, and we get b is equal to 1. Now let's do some more selective choosing. If we make p equals 0, the b disappears. And so that means we'll get m equals m minus 0, so just m a, and a is also equal to 1. So that means that we've got little ones right there, and we can substitute this expression in for that one, but we gotta keep having our dp. So we'll get a over p plus b over m minus p dp, and we can integrate this right away. We're just going to get a kt plus c, and then when we integrate, oh sorry, I should just put the ones right there. I don't know why I put the a's and b's. Remember, those are ones. We solved that. And so this is going to be the natural log of p minus, because this minus comes out of the bottom, the natural log of the absolute value of m minus p, and the c is taken care of over on this side. So we get this, and now we can simplify these log expressions on the next screen. We can actually simplify them to the natural log of p over m minus p is equal to kt plus c. And just for simplicity's sake, later on, what we can do is we can flip this fraction. We'd get a negative out in the coefficient, because there would be a negative in the exponent, and then we'll bring the negative over to this side. And so that will be the natural log of m minus p. You don't have to do this, but you'll see why it makes it easier later on, because you won't have to you'll just be able to multiply a p over. And then, like with logistic growth, or not logistic growth, that's what we're doing right now, with natural growth, and we'll use our properties of logs, and we would get e to the negative kt plus c, and then there's just the property that you can bring the c down. Just trust me, again, on that works. There's also a proof for it in your book in this section for why it works, but it works. And so then we'd get m minus p over p is equal to c e to the negative kt, like that. Then what we can do is we can multiply the p over, and so we can get m equals pce to the negative kt plus p, and then what we'd be able to do is factor out a p, and we'd get ce to the negative kt plus 1, and then we get, finally, we come down to it, p of t is m over ce to the negative kt plus 1. So your book replaces, for some reason, the variable c with a. Doesn't matter, they're both constants, they both mean the same thing. But so this is the general solution to your logistic growth formula. And also, we can write out an expression for c directly. You can solve this, but I'm just going to tell it to you. It's pretty easy to solve. But you'd get c is equal to m minus the initial population over the initial population. And so that is also the general equation for what c means. But that's the general logistic growth equation as a function of p, and not as a differential equation. So we're going to do one problem with this. After you get through this differential equation solving, actually plugging in values for this is really easy, but I'm just going to show you how to do that, and we're not going to do this again. We're just going to jump straight to the formula right here, but we're going to do that on the next screen. So first, okay, so we're going to be doing number 4 from page 637 in your book, and we are given this logistic growth formula that we're going to need to put in a way that looks familiar to us, and we are told that the initial population size is 50, and part A asks us what the carrying capacity is. So the first thing we need to do is just rearrange this formula so it looks the way we want it to, with the kp times 1 minus p over m, and whatever the p is over is going to be the carrying capacity. It's going to be the m. So we can write out dp dt is going to be equal to, we can factor out a p and a 0.4. So that will give us, once everything is said and done, you can do this algebra, it's going to give us 5/2 p times 1 minus 0.001 over 0.4 times p, and that will be equal to 5/2 p times 1 minus, and then you flip this over and put it under the p, that's going to be 0.4 over 0.001, and that will be p over 0.0004. Really small number. So that is our m right there. So the part C, which is the part that we want to focus on, it asks us, when will the population the population be 1/2 of m? So what we have to do is we have to go, if this is a free response problem, you would have to solve this differential equation, but since we've already done that in this video, we'll just jump straight to our model for our solution, general solution for logistic growth, and we will plug in some numbers. Alright, so here we've written out all the information we know. We've written out our general solution, we've written out our solution for C, and so what we want to find is when the population is half of the carrying capacity. And so half of 0.0004, so we want to know when it's 0.0002, and so that's going to be 0.0004 over 1 plus C, we'll figure that out here, times e to the negative k. What's k? Well, we've got the k right here. The k comes out of the equation, so it's negative 5/2 t. So let's come out here, let's solve for c. So c is going to be equal to 0.0004 minus, what's the initial population? Well, we're given that in the question. The initial population at t equals 0 is 50. So minus 50 over 50, and this is going to be equal to 4.9996 over 50. So we can rearrange this. We can multiply this denominator over here, divide this over here, and we will get 1 plus the c, which is 4.9996 over 50 times e to the negative 5 halves t, and this will be equal to 2. We subtract the 1 over here, we're going to get 4.9996 over 50 times e to the negative 5 halves t equal to 1. And now we can multiply or divide this over, and we will get e to the negative 5 halves t is equal to 50 over 4.9996, and we can use our property of logarithms to figure out the t, because we want the time at which the population is half of the carrying capacity. So we take the natural log of both sides, and then this will become an exponent, and then we can divide the negative 5 halves, and that all will give us negative 2/5 is equal to the natural log of 50 over 4.9996, and that is the time at which the population is going to be half the carrying capacity. So that is logistic growth. I hope that that was helpful with all your problems. Thanks for watching, and stay tuned for the rest of Chapter 9, where we're going to be going deeper into differential equations for single variable calculus. So thanks for watching.